All right, let's dive into one of the most incredible things humanity has ever built, the Large Hadron Collider. Seriously, this thing is a machine of pure superlatives, and it was built to tackle the biggest questions you can possibly imagine. But first, you gotta ask the obvious question. Why would anyone build a machine this big? I mean, think about it. It's a circle nearly 28 kilometers around, buried 100 meters underground. The scale is just nuts. What could possibly be worth all that? Well, the answer is just as big as the machine itself. The goal is nothing less than to solve the deepest, most fundamental mysteries of our universe, to basically recreate the conditions a split second after the Big Bang and see what pops out.
Okay, so to get why we need this thing, we have to talk about what's called the Standard Model. It's kind of like our best instruction manual for how the universe is put together. But there are some huge glaring holes in it, some big questions it just can't answer.
This is basically the most wanted list for physics. I mean, look at these. How do particles get mass? That's a pretty basic one, right? Or what about dark matter, this invisible stuff that makes up a quarter of the entire universe, and we have no idea what it is? These are the giant puzzles that the LHC was built to crack. So, you have these universe-sized questions. What do? Well, you build a universe-probing machine to match. And the engineering behind this thing is just mind-blowing. At its core, the LHC is a giant, circular racetrack for particles. And when I say giant, I mean it. We're talking 27.6 kilometers all the way around. Two beams of protons fly around this ring in opposite directions, getting faster and faster. Now, to keep those protons on the track, you need magnets. Thousands of them. And not just any magnets, superconducting magnets. But here's the catch. For them to work, they have to be kept at 1.9 Kelvin. And just so we're clear, that's not just cold. That is colder than the empty vacuum of deep space. And why go through all that trouble? Because that extreme cold lets them generate a magnetic field that is absolutely staggering. 8.33 Teslas. That's over 100,000 times stronger than the Earth's entire magnetic field. You need that kind of muscle to wrestle a beam of protons into a perfect circle when it's moving at nearly the speed of light. And all that power is containing beams that are just insanely energetic. At full tilt, each beam has 362 megajoules of energy packed into it. That is enough raw energy to melt half a ton of solid copper in an instant. So, yeah, precision is kind of important. To see the tiniest things, you have to build the biggest, coldest, most powerful machine imaginable. And just to put it in perspective, look at this. When you compare the LHC to the machines that came before it, like the Tavitron, it's not even a fair fight. Look at the energy, the beam intensity. It's a completely different animal. This wasn't a small step up. It was a giant leap into a new era. Okay, so we've established that this machine is an absolute beast. But how does it actually do what it does? How do you get from a bottle of hydrogen gas to a collision that can change our understanding of the universe? Well, you don't just dump the protons into the main ring and hit go. It's more like shifting gears in a high-performance car. The protons start their journey in a series of smaller accelerators. Each one gives them a kick, boosting their energy before handing them off to the next, bigger one. This whole warm-up lap is called the injector chain. Once they're revved up, they get fired into the main event, the big ring. In there, powerful radio frequency fields accelerate them up to, get this, 99.999991% the speed of light. Then, those powerful magnets we talked about squeeze the beams down to a point thinner than a human hair. And then, bam, they're smashed head-on into each other inside detectors the size of office buildings. And that bam, that collision, is the whole point. The energy is so intense that for a tiny fraction of a second, you create a fireball of exotic particles. Particles that haven't existed in our universe since the first moments after the Big Bang. It's like a tiny time machine. So let's circle back to that huge question, the number one reason the LHC was built. Why does anything have mass? I mean, why does stuff have stuffness? Why does it weigh something? Well, the theory had a wild but elegant answer. There's an invisible energy field that fills every single nook and cranny of the universe. It's everywhere, all the time. This is called the Higgs field. And trust me, you want this field to exist. Without it, every particle in the universe would be massless, just zipping around at the speed of light. Nothing could ever stick together. No atoms, no planets, no you, no me.
The Higgs field is what gives particles mass when they interact with it. It's literally the reason the cosmos as we know it could form.
And don't just take my word for it. The scientists who built this thing were crystal clear from the start. This wasn't a side quest. Finding the particle that proves the Higgs field exists, the Higgs boson, was mission number one. It was the last missing piece of the puzzle. But finding the Higgs wasn't the only thing on the menu. The LHC is also on the hunt for even stranger things. It's looking for the particle that could be dark matter. It's testing theories like supersymmetry, the idea that every particle has a secret heavier twin. And it's even probing for the mind-bending possibility of hidden extra dimensions of space. Yeah, really.
And that's the truly amazing thing here. Finding the Higgs boson back in 2012 wasn't the end of the story. You don't build a machine like this for a single discovery and then go home. It was just the beginning of a whole new chapter. You should think of the LHC less like a finished product and more like an operating system that's constantly getting updates. It's an evolving platform that scientists are always improving to push the boundaries of what's possible. This is literally their upgrade roadmap. They plan these long shutdowns, which are basically like a Formula One car pulling into the pit for a major overhaul. They take it offline, install new hardware, boost the power, and get it ready for the next run, more powerful than ever. And the next big phase, the high luminosity LHC, is going to be a total game changer. Basically, it means they're cranking up the number of collisions a lot. It's going to let them collect 10 times more data than they did in the entire first decade. That's how you find really, really rare things. It's like turning up the brightness on the universe to see what's hiding in the shadows. Which really leaves us with one last kind of profound thought. We built this unbelievable machine to get answers to our biggest questions. But maybe the true sign of a great experiment isn't just the answers it finds. It's the brand new questions it teaches us how to ask, the ones we don't even know exist yet. And that is what this is all about.